Okay, I'm Alex Healey from the University of Melbourne, and today I'm going to talk about some work we've been doing in Boyd-Hollenberg experimental group, where I've been working closely with JP Tietjen, looking at using nitrogen-vacancy sensor ensembles in diamond as a vehicle to enact hyperpolarization of nuclear spins outside of the diamond. So I'll begin my talk with some background of the problem and then introduce some modeling work we've done, basically looking at the overall prospects for this technique in a sort of somewhat idealized scenario. And then this will lead into some more experiments or some more recent experimental work we've done, looking at where we currently sit in the real world relative to the visions of this modeling. So our goal is to hyperpolarize nuclear spins in molecular samples. And what this means is just basically engineering distribution of nuclear spins that is more polarized than the thermal Boltzmann levels, which are typically very small. And there's a big drive to achieve this in the nuclear magnetic resonance or NMR community, because an NMR measurement derives its sensitivity from the degree to which the sample it's analyzing is polarized. So when you perform a measurement on a hyperpolarized sample, you get a big signal boost compared to the thermal sample. And this is commonly done in NMR today, but it is not a sole field. So people are always looking at better or more efficient or more versatile ways to enact hyperpolarization. And generically, the way this works in general is just you have some convenient polarized source that you can conveniently couple to your target in order to polarize it. And for this talk, we're going to be looking at the prospects for using the negatively charged nitrogen vacancy center in diamond as this polarized source, because we can easily polarize it, its electron spin at room temperature. So the only real piece of NV specific physics you need to know for this talk is this polarization pathway and the fact that we can get this at room temperature. So schematically here, I've got the NV ground state, which is a spin triplet, but then when we expose it to green illumination, we can efficiently optically pump it into the ground state m equals 0 state. And like I said, this works well at room temperature, and this is really the main driver for wanting to use NVs in this way, because a lot of other techniques aren't operable at room temperature. And what we aim to do here is couple our shallow NVs to arbitrary nuclear spins outside of the diamond, donate this electron spin polarization through some interaction, and then reinitialize the NV using this green laser pulse, and then repeat this protocol until we build up the sort of polarization that we want for a subsequent NMR measurement. And together with the room temperature operability, NV is an appealing candidate for hyperpolarization, because it has almost zero technical overhead compared to some other existing sort of brute force techniques. We don't need low temperatures, we don't need high fields, we don't need really powerful microwave sources to drive our spin resonance with nuclear spins. And we also have an advantage in that we can couple to completely arbitrary nuclear spins. So there are other existing techniques that also don't require low temperatures and so forth, but typically they rely on some specific polarization pathway which may not be equally applicable to arbitrary nuclear spins, and I might touch on that later on. So these are very appealing positives for NV. However, it does come at a cost, because our spin defect is embedded within the diamond lattice and we want to polarize spins outside of the diamond. We're necessarily in a very weak coupling regime compared to other techniques, which means slow polarization transfer. And this is just because of the large distance between the NV and our nuclear spins we want to target. And along similar lines, we have to interact over a 2D interface rather than in a more efficient three-dimensional sense. So basically, these are pretty big drawbacks, and the purpose of this work is to ascertain whether these drawbacks can be realistically overcome in order to find a niche for NV-based techniques in the existing hyperpolarization landscape. So that takes me to our modeling work now, where basically what we've looked at is steady state solutions to this simple equation, where we have a polarization supply rate, which we basically choose based on realistic near-term estimates for various NV parameters. We have a polarization loss term, which is just the nuclear T1 relaxation. And then we have some diffusion. And yeah, we plug this in and see what comes out. The first thing we notice when we do this is that because we exist in this weak coupling regime, basically any diffusion at all, even just spin diffusion on a solid lattice, is enough to take the bulk of the polarization that we generate away from the NV, which is not a problem in itself, because in general, you're only going to care about the total polarization you generate, not where it is. But this is an issue if we want to interact with or probe the polarization we generate with the same NVs that we use to polarize. So this will be worth keeping in mind for later. The second thing we notice is that because we have to interact over this 2D interface, and we can only interact with spins within, say, 10, 20 nanometers of the diamond surface, we're just not going to be able to efficiently polarize sample volumes relevant for traditional NMR in this geometry. So that sort of microliter scales and up. So this is the first problem we sort of need to think about. The obvious way around this is to structure the diamond so as to maximize the contact area between our shallow NVs and our polarization target. So we look at this sort of geometry where we have a polarization cell built up of two sort of structured diamond slabs that allow us an NMR relevant target volume to be present within these sort of grooves. And we do a parameter sweep of what this would need to look like in order to achieve the sorts of levels of polarization we would like. When we do this, what we find is that to obtain decent levels of polarization, we really need dimensions on the order of 1 to 10 microns, which is pretty challenging. However, not completely inaccessible, because, for instance, microfluidic structures are often already fabricated on something close to this scale. So although this is a big challenge, this isn't a death knell for the technique. There's a reason to believe that if we can show that the physics works well, then this is something that could be addressed further down the line. But placing this limitation on it does mean that realizing this will be sort of a longer term goal. However, traditional NMR is no longer the only way to do NMR. Notably, you can also do NMR using the NV center. So this is naturally sort of an appealing avenue to see if NV-based hyperpolarization can bring an advantage. So I'll have to introduce that briefly. So this has been around for close to 10 years now, where in the first instance, you can think about just using shallow NVs to probe very local NMR information. So the same sort of shallow NVs that I'll look to use to polarize. In this regime, because you're measuring a very small volume, you're dominated by statistical polarization to begin with, and what you do is you measure this using an AC magnetometry sequence where you pulse your NV spin so as to lock in to a desired nuclear signal and decouple from everything else. And in this way, your measurement is limited by an NVT2 up to around 100 microseconds in this regime. Because you're limited by NVT2, you don't get much spectral resolution doing this compared to traditional NMR, but you do get spatial resolution. So shown by this more recent work where they have an ensemble of NV centers and read out in a wide field manner. They get a sub-micron resolution, in this case, looking at these fluorine squares. And if you do something more like this schematic where you have a single NV, in principle, you can get close to atomic resolution in sort of single molecule targets. So that's the drive to use this sort of NV NMR. So the question is, can we get a boost in signal using NV-based hyperpolarization? Unfortunately, when we look, the answer to this, the answer is really no, because we're in the statistical polarization regime to begin with, i.e. what you look at at room temperature using this sort of NMR is not actually the thermal polarization. You have to work quite hard to generate a hyperpolarized distribution that actually gives you a better signal than just the statistical polarization. We also have this diffusion problem that I talked about at the start working against us here. If we have a bulk sample, most of the polarization you generate won't actually remain local to the NV. But it turns out actually even if we can look at a confined geometry in say 2 dimensions, like a 2D film or approaching the single molecule limit, you do gain a raw signal boost, but when you take into account that your measurement duty cycle is diluted because you have to spend time polarizing every time, it turns out your total signal to noise is always less than it would be otherwise, which is what's shown for a variety of parameters in this right plot. So basically hyperpolarization is just no good here, which is a little bit disappointing, but this is not the... There is a more promising regime, which has been developed more recently, mainly at a group at Harvard, but other groups too, where what you do in this regime is you use a thicker NV ensemble with a mean depth of tens of microns in order to access a much larger sensing volume of that same order, tens of microns. And in doing this, because you access a much larger sensing volume, you are in the thermal polarization regime, so we can immediately expect that it could be possible to gain sensitivity advantages by hyperpolarizing this target. And even more promisingly than that, this is naturally operating on the sort of scale that I highlighted before as the sort of amount of confinement we wanted to have in traditional NMR to have the NV-based hyperpolarization to find use. So because you use much deeper NVs here, you get a much weaker signal than if you use shallow ones. So you have to do your measurement a little bit differently. Example pulse sequence is shown here. What you do is now because you are in the thermal polarization regime, you can hit your nuclear spins with a pi-2 pulse so that they process and undergo a free induction decay. And now rather than doing a single NV magnetometry sequence like in the last slide, you do a number in sequence. And your signal then is the variation in fluorescence from sequence to sequence, which the frequency of that oscillation is then related to your target signal. And the advantage here is that you're not just limited by your NV T2 now, you're limited by the nuclear T2 star, which if you choose an appropriate sample like a liquid, can be much, much longer, order seconds at room temperature. And so this gives you the potential to get much better spectral resolution. And they were able to demonstrate in this work a couple of years ago that at what in NMR terms is quite a low magnetic field of 90 millitesla, they achieved chemical resolution. So this is a reasonably promising technique and an appealing niche for us to work with. And indeed, the Harvard group has already demonstrated that they can integrate traditional hyperpolarization techniques with this technique. So they started with Overhauser DMP technique, where they essentially just drive a spin radical so as to transfer polarization. This isn't that efficient in this regime, but they do see a 2 order of magnitude enhancement over thermal polarization at this very low magnetic field, and they see a signal boost over a low baseline. And then more recently than this, they use this para-hydrogen-based technique, where para-hydrogen is just the singlet state of molecular hydrogen. And through a reversible chemical reaction mediated by a catalyst, you can transfer polarization to a target molecule. And doing this, they got 5 orders of magnitude enhancement in these same conditions, which is really a pretty cool result. But naturally, because it requires this very specific chemical reaction, it's not going to have universal applicability to arbitrary nuclear targets in the way that we hope NV-based hyperpolarization will. So this is a cool result, but not necessarily a final result. So we can imagine a sort of simplified geometry where we take the same diamond that you're already using to perform this NMR with this deep readout layer of NVs performing micron-scale NMR. And then you insert a shallower layer of hyperpolarization NVs with the aim of boosting your signal. And the advantage here is that it's a very streamlined setup because all the equipment you already need to do this, you're already using to do the NMR experiment. And when we crunch the numbers on this, we find that the geometry does work out pretty favorably, and we can hope to get multiple orders of magnitude enhancement in this regime, even without the sort of structuring that was structuring of the diamond surface that was going to be required for the traditional NMR case. So this is strong motivation to then look at the experiment and then see where with current technology we sit relative to the parameters that we were putting into this model. So that takes me to my experiment now, where basically my work has been to take previous results that a number of groups came to a couple of years ago, including one at the University of Melbourne, or our group, that did successfully demonstrate polarization transfer using single shallow NVs. And I want to scale up this result to using a dense NV ensemble, which is really necessary whether we're targeting traditional NMR or NV-based NMR. We want as many NVs participating in the polarization process as possible. This is not going to be a trivial extension because for a couple of reasons. The first one's pretty obvious, that as we move to an ensemble density of NVs, we have to add a lot of nitrogen to the diamond. And this is a major source of spin noise. So we're really going to reduce our NVT2. And so part of my work is to probe the dependence on T2 of the polarization process. And the second issue is that we require the negative charge state of the NV defect in order to sense or polarize. And this is just typically not stable near the diamond surface, because there are defects at the diamond surface that result in band bending that mean it's hard to be charge stable near the diamond surface. It's not necessarily obvious why this is related to ensemble versus single, but that's really because when you use singles, you can find ones that are anomalously good in a sense. In diamond, the charge stability of the defect is not just set by the Fermi level position, but also its local charge density. So it's possible to find ones that are charge stable near to the surface, at least long enough for you to do your experiment, that wouldn't be there on average. Whereas we don't have this luxury when we use ensembles. And so I can show this here, where just using an NV NMR technique, I can measure the NV minus distribution in the diamonds that I'll use in the study to come. And what I find is that I really don't see any NVs shallower than, say, 6 nanometers, even though the nitrogen we implant peaks at about 4 nanometers. And so immediately that's like a 50% reduction in coupling, and even more so if I compare to NVs shallower than that. And in these stars, I just put the reported depths for some of those single NV results, which you see are mostly in this much shallower regime. So we're going to exist in a weaker coupling regime compared to previous results. And then this just shows what I was talking about before, that I want to probe the dependence on NVT2. And it turns out I have a couple of convenient ways to do that, just by choosing different diamonds with different coherence properties and different targets that interact with the diamond surface differently, so as to give a different spin path that's interacting with the NV. So this, I won't talk too much about these results, but this is just to say that I have a convenient way to probe the T2 dependence in what's to come. So our experiment looks like this. We have a single crystal diamond slab with a near surface NV ensemble. And we image over a 50 by 50 micron region that contains roughly 10 to the 6 NVs. And we image the NV fluorescence, which is how we get our spin state information, onto a camera, so that we can make sure that all the NVs in this region are participating as we want them to. And we couple our NVs to a variety of hydrogen targets using what's called the pulse pole sequence, which is a pulse sequence developed at the University of Ulm a couple of years ago, which basically mimics a Hartmann-Hahn flip-flop Hamiltonian when a resonant condition in the pulse spacing is met. So that's what's shown in this plot. As I sweep tau, this pulse spacing, I see a drop in the NV coherence, which we would infer corresponds to donating polarization to the hydrogen spin bath in this case. And we choose this sequence because it's designed to be robust against microwave detuning, and this allows us to access this full field of view. And so the results to come are just average over the full effect of the 10 to the 6 NVs here. This is not the only way to couple NVs to nuclear spins and transfer polarization, but it is what's suiting our current experiment the best. But in future, you wouldn't necessarily be restricted to using this protocol with various advances. So having seen the hydrogen resonance, we now like to look at the dynamics of this process. So that's shown here for our sort of most favorable case, which is interacting with hydrogen spins in a biphenyl crystal, so just a solid lattice. And this red set of data is just one of the T2 curves I showed on the previous slide. So just the background NV-T2 that we see when we drive off resonance. And in the blue data, we see the accelerated decay that comes when we drive on resonance. And in the best case scenario, we infer that the difference between these two sets of data would be useful polarization that we're donating to the hydrogen bath. So we can take this difference, divide through by time to get a polarization rate, shown here, peaking at about 8,000 spins per second. And then compare to a variety of theoretical models where what we see best represents our data is this blue curve, which I call my hybrid model, which is just a sort of phenomenological interchange between coherent behavior at very short times and incoherent behavior represented by this strong dephasing limit at longer times. What representing our data like this gives us is that this peak corresponding to our optimal sequence, how effective, like the magnitude of that peak is related to something proportional to this term in brackets here, which is the total coupling to the hydrogen bath, so proportional to the shallowness of our NVs, but then also divided through by the total dephasing rate of the system. So this is giving us what I wanted to note before, that is that we do expect to see a sharp dependence on NV-T2. And we can see this concretely here, where because I'm able to probe to control for NV-T2, I can see the dependence this has, and the y-axis of this plot here is just taking experimentally observed maxima in the polarization rate and plugging into our theoretical model from before. And what we see is that the signal we get does vary with T2 in the way our model says. And with the best results, this biphenyl data shown here, we see that we are seeing a signal within a sort of order of magnitude of what we were plugging into the model. So this is reasonably promising. And to compare with the Harvard results, this comes out to be about a 2 order of magnitude increase over thermal polarization in the nearest 10 micron from the diamond surface at a moderate magnetic field of about 50 millitesla, which is a higher field than the Harvard results, so a higher relative to a higher baseline. So basically, this comes out being similar to their Overhauser DMP results, or maybe slightly better, which is a promising early result. Not as efficient as their parahydrogen results, but again, that was very specialized to a certain type of target. Of course, we'd like to directly evidence the excited polarization buildup we have, but because of this diffusion problem, this is a challenge. The vast majority of the polarization we generate will not be directly sensible, but sensible because it diffuses outside of the NV sensing volume. Nevertheless, we can try this by driving on resonance repeatedly with our optimal sequence. And what we hope to see is an increase in NV fluorescence, essentially as the magnitude of this dip decreases as some level of local buildup does occur and our effective coupling to the bath reduces. And the results of that measurement are shown here, where because of this diffusion problem, our y-axis is pretty tiny and our measurement is clearly very noisy, but we do see a small rise that is consistent with our model. So while we would like to to probe the full extent of the polarization and have a clear measurement, this is at least supporting the inferences that I'm making up here. So we can move on to something slightly more challenging now, which is to try and polarize a liquid state target. So I don't know if I really mentioned this before, but this is an important thing to address because liquid state NMR is really what the sort of Micron-scale NV NMR I introduced earlier really wants to operate on, because this is where you're going to, because it's a T2 star limited process, and liquid state targets are going to have a longer T2 star than solid state targets. And yet, recent theoretical work from Lee and Paul in our group has shown that pulse polarization protocols like the one we're using are expected to lose a lot of efficiency in this regime, essentially because they only ever approximate a flip-flop Hamiltonian, and this approximation basically breaks down or starts to break down when you have rapid diffusion through the NV interaction region. So I want to look at this by interacting with a variety of liquid targets, but most illustratively, a variety of mixtures of glycerol and water, which should have near identical hydrogen densities, but variable diffusions, variable viscosity. And so in this plot here, with the same measurement as before, I can see that I do see a decrease in the interaction as the diffusion increases. However, the dependence is not as sharp as would be predicted. And for the more viscous liquids, I see an interaction within a sort of factor of 2 of the most of the best solid results we have. So that's a reasonably good result. I will stress the reason why we have a shallower than expected dependence on diffusion in this higher diffusion regime is not, we can't tell unambiguously in our current measurement. But one valid interpretation is that we have some dragging at the diamond surface, which is leading to locally increased or locally decreased diffusion, and hence more efficient polarization transfer that would be possible in the bulk, where these dynamics would be unchanged. So again, future work's needed to say that for sure, but if that is the case, that would really be pretty promising for the prospects of liquid state hyperpolarization using NV centers. So this brings me to my conclusion, where what I've shown is that we have been able to use an NV ensemble for external polarization transfer, and that the best rates we measure are broadly compatible with the parameters that we were putting into our earlier numerical model. And that model showed that if we can get around this problem of having to structure the diamond in a certain way, that our technique could be relevant for enhancing traditional NMR. And even without this sort of structuring, we can hope to find a good niche in the NV-based Micron-scale NMR. And so for future work, we want to move towards implementing this, move towards this all-in-one diamond hyperpol plus NMR spectrometer. Not least because it will allow us to actually probe the full extent of the polarization buildup that we're creating and improve on that measurement that I had on the previous slide. And the last thing that's really clear from the work that we've done is that, of course, we're going to want to increase the polarization rate that we're producing. And what's really holding us back at the moment are mainly diamond material properties. So we need shallower NVs and we need more coherent NVs. And that's really going to come from some material science, looking at the diamond surface and looking at engineering the spin properties of the diamond lattice, the charge properties of the lattice, in order to make things more optimal. So this is something we're looking at and other groups are looking at. And there's reason to believe that continued improvement can be found here in order to make the prospects better in the coming years. So with that, I'll thank you for your time and the people involved in this project. So this is an older photo now of the broader Hollenberg group, but we had Liam Paul and Greg White help us out with some theory. We have collaborators on this project at the School of Chemistry, obviously Lloyd, a supervisory project management capacity, and JP,